I will go to the point. Our perception of reality is expressed in our understanding of the matter. Being like that, actually, our concept goes farther than what we can see. As we know, the matter is made up of atoms. Both in the electronic cloud and in the core of the atom, we can identify more elementary units of particles. Some of them are the quarks, units of protons and neutrons, and the leptons, like the electrons and neutrinos. In general terms, according to quantum physics, we can identify two kinds of elementary particles. These are fermions, a group of massive particles that carry matter, and there are bosons, massless particles of exchange of energy that take part in the fundamental interactions. Let's see. In our universe, there are four fundamental forces that act in all the physics known phenomena. Particle physics explains that in each of these forces, there are boson particles that carry the energy to exchange it between matter particles, also called fermions. For this, the particle physicists created an information scheme called the Standard Model, a table that assembles all known fermions and bosons particles and their properties. In the 1960s, scientists Weinberg, Salam, and Glashow proposed the union of the electromagnetic force and the weak force in a greater force called the electroweak force. How they came up with this? Well, they start with a curious observation. The particles of the electromagnetic force, the photons, are bosons of mass zero, whereas the bosons W and C of the weak force are massive particles. These three scientists proposed that in a few millionths of a second after the Big Bang, when the universe was at very high temperatures, the particles of these forces were essentially identical and were part of a single major force, the electroweak. When the universe began to get cold, both particles separated by what is called a spontaneous rupture of symmetry and acquired different masses and properties. However, this theory was still lacking a factor to understand mass differentiation, a mechanism of rupture. British scientist Peter Higgs postulated evidence of a mechanism known as a Higgs field that permeates all space, a field that appeared in the millionth of a second of the Big Bang as a kind of cosmic broth. So, where is Higgs boson? We can understand easily Higgs boson by using an analogy. Imagine that you have organized a party in your house, so it is full of people. But then, the most popular guy arrives and all the people start following him, increasing his resistance to movement. All these people are Higgs bosons, and their effect on the particles in the Higgs field is what determines the mass. Photons, gluons, and W and C particles are bosons without their own mass. Photons and gluons do not show any mass because they do not interact at all with the Higgs field. On the other hand, the particles W and C interact strongly with the Higgs field, so they show a huge mass.